All right, so today I want to talk about difference of squares. And beyond. So I want to look at a sort of familiar formula that that's a way of calculating the difference of squares, and then I want to see how it generalizes when the power is something higher than 2. So what am I talking about here? Well, here is the formula that you might be familiar with. X squared minus y squared. This is called the difference of squares. I've got two terms. I don't care what they are, so I'll call them x and y. And they're both squared, so x is squared and y is squared. And the difference between them, another way of calculating it, I mean, obviously what you could do is you could square x and then square y and then find the difference. But the formula of the difference of squares says this is the same as finding the difference between x and y and multiplying it by the sum of x and y. This is the difference of squares formula. And the reason why this formula is true is we can sort of work backwards. We can start with x minus y times x plus y and just multiply it out. We get x times x is x squared. And then we get x times y, that gives us xy. Then we get minus y times x, that gives us minus xy. Then we get minus y times y, that gives us minus y squared. These cancel, and I'm left with x squared minus y squared, the difference of squares. So this is pretty simple, and it gives us a nice formula that's actually useful in a variety of contexts for algebraic manipulations. The difference of squares can actually be written as a product of the difference of the two unsquared numbers times the sum of the two unsquared numbers, right? Just for this reason. Now what happens, well, let me leave that up there. What happens if instead I want to look at a difference of cubes? Is there a nice formula for this? And I mean, you might imagine that there might be lots of different formulas, but I want to focus on one in particular, which it's not going to be quite as nice as this, but we'll sort of see the resemblance. And the formula is x minus y times, so it starts off the same way, but now instead of x plus y over here, it's going to be x squared plus xy plus y squared. X squared plus xy plus y squared. Okay, so the first part is the same, the second part looks different. We'll see the sort of pattern in the second part in a second, but first let's check that this actually works, okay? So instead of asserting this equality, let's let me erase this and ask myself, what does this equal? What if I just do it in reverse? I multiply it out. So I've got x times x squared gives me x cubed, x times xy gives me x squared y, and x times y squared gives me plus xy squared. I'm running out of space here, so I'll continue down here. Then we've got minus y times x squared, so minus x squared y, minus y times xy, so minus xy squared, and minus y times y squared, so minus y cubed. And now actually I've written it in a sort of convenient way. You can see that we've got a plus x squared y and a minus x squared y, so these are going to cancel, and a plus xy squared and a minus xy squared, so these are going to cancel, and it leaves me just exactly with x cubed minus y cubed, which is what we wanted. So I'll write that again over here, x cubed minus y cubed equals this. This formula is a sort of generalization of the difference of squares formula, but now it's a difference of cubes. And we still have the x minus y kind of factored out, and then this thing inside here. What's going on? It's the same kind of thing that happened up here. Up here we had a cancellation of the sort of inside terms, which left us just with the x squared and the y squared. And here, instead of having two things canceling, we have two pairs of things canceling, leaving us with just x cubed and y cubed. So if we pick up on that pattern, we can try to extend this same formula to any power, not just 2 and 3, but any power, let's say k. So let's try to do that. Let's look at x to the k minus y to the k. Draw that a little more nicely. And the idea is this is going to be x minus y times something which I want to end up with x to the k, a bunch of cancellations, and then minus y to the k. So if it's going to be x to the k, I want the first term to be x to the k minus 1. Then when I multiply these two together, I'll get my x to the k. And then if I sort of look at this pattern down here, what happened when I went from here to here is I lowered the exponent of x by 1, and I increased the exponent of y by 1. You can think of y as being here with an exponent of 0, because y to the 0 is 1. So I can follow that same pattern up here. I can say plus x to the k minus 2, lower the exponent by 1, y, plus x to the k minus 3, y squared. And continue that pattern all the way to x squared times y to the k minus 3 plus x times y to the k minus 2 plus y to the k minus 1. And I'm ending at exactly the point I want to end at, because this minus y times y to the k minus 1 is going to give me my minus y to the k. And the hope is that all the in-between stuff is going to cancel out. Okay, so let's check that. Let me erase this and start from this product and figure out, well, what happens if I actually multiply this through? Well, I get x times x to the k minus 1. That's my x to the k. Then I get x times x to the k minus 2y. That gives me plus x to the k minus 1, because it's x times this, so the exponent's going up by 1, y, plus x times x to the k minus 3, y squared. So again, this x multiplied by this term raises the exponent of x by 1. I'm multiplying it by x one more time. And so on. And then we get x cubed times y to the k minus 3 plus x squared times y to the k minus 2, and finally plus x times y to the k minus 1. That's just going the first pass of multiplying x by everything. Now I'm going to multiply y by everything, or rather minus y. So I've got minus y times x to the k minus 1. Well, that's just x to the k minus 1 y. Once again, I'm writing it sort of strategically below. Now minus y times this gives me minus x to the k minus 2 y squared. This is this y and this y combined to give me y squared. And we can see we're getting exactly the cancellation that we want. Now this times this is going to give me minus x to the k minus 3 y cubed minus minus y times this, so minus x squared y to the k minus 4, y to the k minus 2, right? This minus y times this here is giving me x squared, and then the exponent of the y goes up by 1, so it's k minus 2, minus x times y to the k minus 1, that's minus y times this term, and finally minus y times this last term gives me minus y to the k. And once again, we've got this cancels with this, and this cancels with this, and this cancels with this, and this cancels with this. All of the middle terms cancel, and I'm left with x to the k minus y to the k. So what I have, writing this back in here, x to the k minus y to the k, I have a more complicated, but still sort of pleasing, there's certainly a pattern here, formula for not just a difference of squares, but a difference of cubes, or a difference of powers of 4 or 5, or a difference of powers of k for any k. And it looks like this.